Bismillahirrahmanirrahim. Hello everyone. This is another ABAQUS tutorial. In this tutorial, I'm going to show you how to model a corrugated steel plate shear. So, in case if your research is steel plate shear wall and you know about the corrugated steel plate shear, sometimes to increase the stiffness of the structure, stiffness of the steel plate shear wall, so then we uh, create some innovation and make it corrugation or corrugated. So this is an example which has about 1.9 from center to center of the column and also 109 center to center of the column. If I go to use dimension and let me use linear. So this is 200 and totally 100, 200, which is about 118 to center. So totally the height per width height per bay or length is 1. The thickness of this steel plate shear wall we will discuss later, and this is the cross section. We're using a I section, and the steel plate shear wall is welded to the boundary elements with a fish plate. In the modeling, we will assume this is a weld connection and it is not considering the fish plate. This is example result, but before let me show you how we can model this. So we have three choice to model this. One is using for the boundary element beam element, and also solid element and shell element. So whatever you want, you can do it, but you should consider the accuracy of the modeling and also preferred method. So now we have in the modeling uh, four we have four parts. So one is the beam, and this is the beam. If I go to here, edit, and you can see the length is 2 meter, and you can see the cross section is 200 flange size and 200 height. So the shell extrusion, the type is shell extrusion. So, okay, and next we have the corrugated web plate or corrugated web plate. So this is the corrugated web plate. It's a little difficult to model in here, but so the size is, the height is 160, and you can model using a line, such as you can come here and then come back and here like this. But I recommend you to model that corrugated line in ABAQUS. Sorry, in CAD, and then you can import this line as a here you can see here as a part, then you can bring that part and then extrude it. So then you can extrude, depth is 106 meters, 1.6 meters. So the same for the column. We can go here. For simplicity, the column size is, the height is 2.21 meter and the size is same as a beam. Now we go to the assembly. Sorry, in the properties. So we use this steel material. We have two kind of material. Mostly we used high strength material for the boundary elements and low yield point materials for the web plates. So I'm going to select web plate. We have the density the unit is millimeter, megapascal, so this is the plasticity. And for the steel beam, we have this one, and it's a little higher strength. Now we have a flange thickness, web thickness, and shell plate thickness. So the web plate is 1 millimeter, and the corrugated web plate 1 millimeter. The flange thickness is 8 millimeter, and the web of the beam column is 6 millimeters. Here is one thing you can consider: the uh, integration point across the thickness of the shell elements. Now we can go to the assembly. So for assigning, it's not difficult. Just you can go here. This is a column. It has a web and flange. So this is the flange thickness. So this is the flange, and flange is selected, and the second part is web plate. So I will upload this model in my channel description. You can download and see how it's worked. Go to the assembly, and we bring all the uh, beam columns, and we will connect like this, adjust together, and using the merge, we're using the merge to make a single elements. So that means we have uh, created some stiffener, and as well as the web plate also orientated in the middle of this beam column like this. If I go to view display the rendering of shell, and you can see it's like this. And here is, so now so instead of we use any sort of connection between this, so we assume this is a weld connection, and created one single fillet weld by using merge method. So now we can go to the step. The first step, we should utilize the post-buckling of behavior of the steel plate shear wall. So we need to consider in the second analysis, or the dynamic analysis, or the static analysis, the amplification of the web plate. So therefore we need a buckling analysis to see the buckling of the beam, and then we will use some mode with scaling uh, in the next analysis. So for we created the buckling, and we go to the buckling and request 3 buckling mode, and you can give a maximum iteration 200 or 100, so it will can finish that way. We go to the interaction, so we created one point here. You can use this here, and from this point here you can create one point offset, and then define a set and a reference point, and then create a set called displacement or control point. So this is the control point you can see here, and then use a coupling method to couple these points with this region. So instead of applying load in the direct to the edge or the element, so we will take a little offset, and then we will apply that point. And now we can go to the load, and we want to see the loading procedure. So we assume this area is fixed base connection, and here fixed connection, and so mostly we cannot, this still is a very ductile materials and ductile structure, so we need a lateral support when during the loading gets happened. So there is a lateral support such as a slab. So the slab can be a diaphragm and can keep the structure stable in the lateral displacement. Now we want to create a lateral displacement as well. I selected this area, which means in practical there is another beam which extended to here and here as well. Now in the backling, I want to instead of applying load, backling load, I want to apply a displacement. So a displacement. So now the displacement is giving 1 unit in that control point, and we want to for 1 millimeter control point, how much the eigenvalue should be. So then the eigenvalue times the displacement, and we will get the total force which is needed to create backling in this structure. Now we can go to mesh. We can give a proper mesh. Here, let me show you. I have used 14, so you can conduct a sensitivity mesh analysis and see which mesh is quite good. So, and one more thing, then you can consider one in the element type. Mostly we called reduced integration, so that can keep the structure to converge during the analysis. And we can go to job and create a job. So the first is called backling. So I should write backle. So previously I have modeled this, and I'm going to call backle 1, and here, and I said submit. Now it's running, and it will take a while to get complete. So I'm going to back here, and you can see the already result is out, and this is the first smooth shape which caused this wave plate create this sort of backling. So this is the eigenvalue. This eigenvalue is times by the displacement, and we will get the work done. So now we can after to see how much when we push this to 1 millimeter and how much force needed. So we will make times by this, and then that will be the backling load. Next we can go to see the second mode, third mode. So after the backling analysis completed, and we can go to copy this model, go to model, copy model 3. So I already copied as a model 2. In the model 2, the first thing is that you should delete the backling analysis. So instead you can use another available method. So here I used static general. In a static general you can give a time period. So this time period is based on the cyclic analysis, which is about now you can divide it by 60, so about 6 seconds, 6 minutes or 5 minutes. So the total time required to complete to 4% drift of this structure. So here is amplitude. So the first is I want to 1.6 millimeters, and the second 2 millimeter, 5 millimeter, 10 millimeter, 20. So there is a code. It's called ATC24, which is mostly uh, and giving some information regarding to the cyclic analysis and experimental research you can use there. So they will recommend us to consider uh, 3 circle in the elastic region and 2 circle after in the yield part. So delta yield, we have 2 delta yield and we have 3 delta yield. So you can maximum 2%, 3% of the drift. So this is maximum 80 millimeter, which is about 4% of the drift. So 4% of the drift, 2 meter, and it become 4%. And the total time period is 1,500 seconds. So you can reduce, you can increase. This is a function you can play with this and get a better result, and that can match your experiment. And here you can go to the increment and give a large number to finish until that 1,500 second, and the initial should be a little small, and this will be minimum and this will be maximum. You can give 10, 20. This is done, and we can create some output. So the output, we can select a pre-selected, and also we can reduce the time of the analysis by changing the output size and also the output numbers. Next, we want to go to the create some time history output. So the first time history output is here is the energy. So we'll first see this one, which is almost all kind of energy is with all kind of energy is available to consider in the time history output. So as example, I want to see the some of them, such as let's go to plastic dissipated energy, because in this system we use the plasticity or post-buckling behavior of the wave plate. So that means after the wave plate is yield, we want to use that phenomena to dissipate energy which during an earthquake. So now you can, if you consider also the time of duration, the time duration will be increased. If you reduce, so that will be faster. You can select which of them you want. So I'm gonna using this uh, let me use PD and this elastic and total energy. You can also constrain energy as well. And now here is, we previously defined this point as a controlling point, and we want to use that controlling point to get the reaction force and displacement from that point. So therefore we select the U1, which is this direction, and REF1, which is in this direction, reaction force, horizontal reaction force. Now we finished here, we go to the interaction. The same, we need one interaction and also a load. In the load we can consider some gravity load in case if you have, but I suppose I don't have here. And now here is the displacement. In a previous we called buckling load, so now we want to create a displacement using one unit in this direction and using this amplitude which is previously defined, and the same other is from the previous initial step fixed and U3. So the mesh is also the same mesh. In the job, we go to the job and we create a job and called Cyclic. We already defined this Cyclic. Create Cyclic analysis, and we can submit our job, and we're going to submit. Okay, now which we in the first step we giving the backlink analysis that's completed result, and here is the results of that which is the same we already checked in the buckling analysis. And now we can check the second one, this one. This is called aborted. So let me check what's the problem. Here is the error that's called aborted. So OD file, the database is from a previous. Yes, here is one thing. We should consider that amplification. So we go to check this model. Go to keyword. We go to keyword, and here we want to write an imperfection called file and then backlink. So now I have created one more. So I'm going to use this one, this backle one. So I can call it here backle one, the same step, and considering mode 1, mode 2, mode 3. This is a scale factor. You can consider 1, 10 like this, but there is some you can consider to 15 is good. So you can use to 15, but there is a very numerical example which is depends on the thickness of the web plate and also the height and weight of this one. So you can consider 0.1 of the height, 0.1 of the height. So if height is 2 meters, so then it can be 2 meters and it can be 20. So you can consider 20. So this is a very logical, and you can get a better result. And also you can do some analysis like use 5, 10, and see what's the difference. And now okay, and this problem will solve. Now we can check. Here is the checking. So it works and there is no problem. So it need about hours to finish, but we have already analyzed called Cyclic analysis model 2, and I'm going to see the results. Okay, this is the result, the cyclic step, and after 7,800 increment, and it reached to finish. This is the stress strain visualization. I'm going to here to check legend show. Here you can see it's already reached to the ultimate because this area is failed, and we can see other. Let's go to see the active yield. So mostly that web plate is yield. If I go to back a little, and you can see here. So in the beginning, so mostly the web plate is yield. So that yielding caused to use the post strain of the structure with steel plate, and then finally the maximum stress is also concentrated in the panel zone, and finally here created the plastic hinges in the column and fail. So one thing that shouldn't in practical model or construct is the column and beam shouldn't be same. So mostly the column should be quite strong and the beam should be weak. So this is the principle of designing such kind of structure. Now you can go to plot the two data. You can select, go to here, and from output, and you can go to reaction force and this one. So this is the displacement curve, and then you can combine and plot it as a is-stress curve. So this is the displacement and maximum AT, and this is the force maximum 500 kilonewton. You also can go back here and see some dissipation energy. So I'm mostly interested on the plastic damage, plastic dissipation energy, because we utilize the post-buckling phenomena in this plate. I'm going to plot it, and you can see this is the energy dissipation. So quite a large amounts of energy is dissipated. So you can suppose it's about 50 uh, 50 kilojoule. So this is very large. So the same other energy dissipation. So like this you will analyze and simulate a corrugated steel plate shear wall. So I will give the INP file. So just you can come to the pods here and comes to the uh, file, and you can import that as a model. So when you import my data as a model, you can come to model and check here INP file, and you can bring that INP file here. So after that you will see the same model, and you can go back to the job and just first click this one, submit. After this finished, you can submit the second one. So after both is completed, then you can interpret the result. So this is all, and if you have any question, please put in the comment and I will find time. If interested to see more advanced topic on earthquake engineering and also especially on ABAQUS simulation, please subscribe my channel and also share, comment and like. See you next time.